All right, thank you very much for the introduction. And it's an honor to be the first presentation of the year, definitely. I hope this brings luck to everybody. Can you see my screen?
Yes.
All right, welcome everybody. Thank you very much for being here. My name is George Markou. I'm an associate professor at the University of Pretoria in South Africa in the structural division. My field of expertise is indeed in computational mechanics, but now lately we started also entering the world of experiments like you do there a lot. And we will talk about that hopefully next year when we have our first results under the research project of China, collaboration of China and South Africa. We got a project in developing smart monitoring system that foresees some experimental work as well. So today I'll be talking to you about reinforced concrete structures under extreme cyclic loading conditions, and of course, how we started developing Formulae through the use of artificial intelligence algorithms by developing data sets. So today I'm going to say a few things about 3D detailed modeling of reinforced concrete structures, and then I'm going to show you some recent results that we got from advanced nonlinear cyclic analysis that use also new proposed damage factors, and then talk a bit about machine learning and show you what we've done so far. Now, when we talk about 3D detailed modeling of reinforced concrete structures, we assume that we discretize the concrete domain through hexahedral elements, usually 8 or 20 noded, and we can also model the cracking within the hexahedral elements at the Gauss points through the Schmier crack approach, and of course, we can discretize the exact positioning of the embedded rebars, as you can see here, and the reinforcement based on the design. So this is ideal for assessing the design that derives from a specific procedure by using any type of design codes. All the numerical analysis is performed through the use of Recon and Fair, which is a research software that I've developed during my PhD and continue to develop, adding new models, material models and elements for the needs, of course, of the research that we perform at my university. You can see the link there. And if you want to find more, just communicate with me and I will happily provide you with more information. Now, a few things about the material model of concrete. It assumes a hydrostatic and deviatoric stress, so we decouple those. And eventually, through the use of the bulk and shear moduli, which have nonlinear and relationships, we can describe the overall three-dimensional behavior. Therefore, we use three-dimensional material constitutive models, and we account also for the coupling effect between the shear and the normal stresses and strains. Now, the advantage of this material model is the fact that we only need to define the uniaxial compressive strength and the tensile strength, and of course, upon isolation, the remaining shear strength after a crack has occurred. So if we have a crack, along the crack plane, we assume a remaining shear strength. And therefore, this is very simple for any type of user to define the material properties of the concrete that they want to model. Either monotonic or cyclic analysis. We had a couple of publications recommending some filters and algorithms in order to stabilize the procedure of opening and closing of cracks, which allow us to perform full-scale structural analysis. And of course, this is very computationally demanding, especially when cracks start to open and close with the unbalanced forces. Things become very computationally demanding and unstable. So through this, we were able to accelerate and stabilize the procedure. In order to assume and calculate, in this case, if we have a cracking opening, we use this failure criterion as is shown here. And of course, in this case, we have the, give me a second, I will activate my laser. Okay, so we have a Gauss point within the hexahedral element, and we can calculate whether we have a crack or not, and the crack is always perpendicular to the maximum principal tensile stress. And this is the material constitutive matrix, which is modified according to the number of cracks that we have. This is the convex strength envelope. And of course, one of the most important parts when you develop new algorithms is the ability to validate if they have the numerical ability, in this case, to reproduce or capture real experimental results. So as you can see here, this is a beam column joint, and different beam column joints were tested by Garcia et al. In 2014. And this is the schematics with the reinforcement detailing. And this is, of course, the way that the load was applied at the column and at the beam. We had an actual force at the column. And this is the beam which was loaded by applying a cyclic load. And this is the figure of the bare joint, reinforced concrete joint, after the completion of the experiment. This is the model that was developed in order to numerically investigate the mechanical response and reproduce the results. Of course, this was not the end of the experiment. This reinforced concrete joint was thereafter rehabilitated and retrofitted with carbon fiber reinforced polymer sheets and then tested again. So we used the newly proposed damage factor for concrete and steel that have the ability to capture the accumulated damage in concrete and, of course, slippage phenomena at the rebar level. These are the two models that were developed for the bare and the retrofitted, in this case, RC joints. And hexahedral elements and embedded rebars can be seen, and also the CFRP sheets as they were discretized for the needs of this research work. These are some data for the mesh details, number of total nodes, elements, and embedded rebar elements, hexahedral elements, and embedded rebar elements that were used in order to model this experiment and this specimen. And of course, the material details, they resulted, and we took them directly from the publication according to the tests that were performed, uniaxial compressive strength tests for concrete. And of course, the high strength concrete was used in order to, as you can see here, rehabilitate this area, this region of the joint that was completely cracked. And the CFRP sheets that were used in order to strengthen the joint after the first set of cycling loads that were applied and led to failure, the specimen, and eventually rehabilitation and strengthening. So as you can see here, this is a comparison between the experimental and the numerical results of the bare joint. This is a delta curve. This was published recently. And of course, not only Garcia Reyes, that was a part there of the team, now he's in Warwick University, also Mauricio and Prof. Pilagudas were included in the team. This work was performed when I was there, a research visitor at the department in 2018. This is the corresponding comparison between the retrofitted joint, and as you can see, the capturing of the maximum expected resistance was done in an optimal manner. If I recall well, this was, it had an error less than 5%. So this is the behavior and the numerical response with the proposed damage factor, and this is the behavior without the damage factors. And as you can see, the hysteretic loops completely change, and this shows, of course, the contribution of the proposed damage factors that provide us with the ability to capture these extremely highly nonlinear problems from the material point of view, of course. This is the animation of the von Mises strains as they resulted from the analysis, and as you can see, the elements, the hexahedral elements of the beam were not added in the view in order to see the embedded rebars and how they deform. And of course, we can see here clearly the damage development in the joint area. Now, this work that I'm going to show you is also recently published, which is a continuation of the work that we did with Mauricio and the rest of the team. Maurizio, right? Not Mauricio. Apologies, I was in Chile, so there the double Z is C. It's a bit confusing, but anyway, they have their own dialect there. So the continuation foresaw, in this case, the development of a new cost-effectiveness method in order to determine which strategy is the best when it comes to retrofitting reinforced concrete structures. So main methods that we use in order to retrofit our structures and reinforced concrete structures is CFRP jacketing, of course, reinforced concrete jacketing, and infill reinforced concrete shear walls. And the biggest problem, let's say the biggest challenge, is to estimate the strength of the retrofitted structural section and eventually the overall strength of the structural member, and then how that affects the overall mechanical behavior of our structure. Given the fact that so far, let's say like Canepe, which is the retrofitting design code in Greece, which is it is considered to be the most comprehensive design code when it comes to retrofitting of structures, uses semi-empirical formulae, design formulas. And of course, it does not allow the designer to use tools and doesn't provide with any tools to investigate the overall mechanical response and effect of the retrofitting intervention to the overall mechanical response of the structure. So here, this is one great advantage that we have through these tools that we've developed, that we have the ability to actually do that. This is the constitutive matrix of the concrete, the material constitutive matrix, where, as you can see, we have DC, which is the damage factor, a proposed damage factor, which takes into consideration the number of opening and closings of a specific crack during a cyclic analysis. So through this damage factor, we are able to directly get the material deterioration of the concrete. And of course, if we have a Gauss point at the concrete, at the material level, which is completely crushed, then we assume that this is the remaining strength based on this material constitutive matrix, where VDAS is the remaining shear strength, and it's said equal to 2.5%. In addition to that, damage factor foresee the use of, again, DS and DR, and of course, DS and DR can be found in the publication. I don't want to overload you with Formulae, and therefore I'm just mentioning them so as for you to know that we have 3 different types of damage factor that are included within the cyclic nonlinear analysis. Now, again, another problem that was modeled in addition to the previous one that I've shown you was the Mahini and Rona in 2011, where they tested again similar type of joint. And as you can see, this was modeled by using the same approach, but part of the beam here was modeled through a beam column finite element. So this is a hybrid model and a hybrid mesh, which uses 2 different in dimensionality finite elements in order to further decrease the computational demand without losing any accuracy. And of course, these are the comparisons between the numerical and experimentally derived delta curves. And as you can see, of course, these the curves are in good agreement. Now, after performing additional validation, we created the finite element model for a 4-story building. This was tested in the surfing project. It was an actual building of 12 meters height, 4 stories. This is 6 meters, and this is around 9 meters. And the idea here was to design a framing system which is not seismically resistant by using the old Cypriot code, which is now replaced by Eurocode, of course, given that Cyprus is also a member of the European Union. And as you can see, this is an infill shear wall that was also constructed, and then this was tested under cyclic loading. And a model was developed in order to capture the experimental results. They applied 3 different rounds of cyclic loading, 0.1 G, 0.25 G, and the final set was, they called them the funeral cycles, given the fact that they pushed this specimen until it failed completely. So what was done here, different models were created by using different CFRP configurations, CFRP sheets, and of course, we use also the infill walls where the rebars within these reinforced concrete infill walls were either steel, glass, aramide, or carbon fiber reinforced polymers. And they were tested by using this displacement history. This shows the total applied displacement at the top floor. Of course, similar displacements lower in magnitude were applied at first, second, and third floor as well, according to the experiment. So the idea was to initially damage, in this case, the specimen, the structure, and then apply, let's call them these final cycles, in order to see how and in what extent, our retrofitting strategies helps and strengthens the overall mechanical response of the structure. Also, we performed some analysis, in this case, in order to show the contribution of the damage factors, as you can see with the black line, the hysteretic loops for the case of the nonlinear analysis without the proposed damage factors, and the red represents the hysteretic loops of, in this case, the case where the damage factors are activated. This was the case of BC205. I will explain now what this means. Now, BC stands for the bare reinforced concrete framing system. So these are models without reinforced concrete infill shear walls. When we have 2, 3, 4, or 5, we assume if it's a 2, it means that only the ground floor was retrofitted with CFRPs. 0 means only the columns of that ground floor were retrofitted with CFRPs. And 1 stands that both columns and beams of the ground floor were retrofitted. And of course, the last number refers to the number of layers that were used, 3 or 5. So if I have, let's say, 303, this means that the ground and, in this case, first floor columns were retrofitted with CFRPs and 3 layers. If I go here to the 515, this means all floors, and 1 means both columns and beams were retrofitted with 5 layers of CFRP. So this was, let's say, the coding system that was used. And RC referred to the structures, the buildings that foresaw infill shear walls. And RC refers to steel rebars, RG refers to glass, A, aramide, and CC refers to the carbon. And there were 2 last models where we applied shear wall only at the ground floor, and here shear wall at the ground and the second floor. So these are the 24 models. And of course, the maximum base shear that derived at the final loading cycles can be seen here for the case where we did not assume any infill shear walls. And as we can see, if we reinforce and retrofit, in this case, the entire building, all floors, the maximum base shear derives. And if we, of course, reinforce both columns and beams, also the strength of the building, the derived strength of the building increases. Now here we can see the hysteretic energy for the entire loading history. And as we can see, this does not apply, and this trend is not found when it comes to the hysteretic energy. We're going to explain that in a bit. Now, this is a figure that shows the von Mises strain contour distribution for the case of the BC505 for different horizontal deformation, positive 23, negative 23, and positive 50 millimeters at the top floor. And as we can see, of course, the change in terms of strains and damage development is clear. And definitely we can also see the advantage of using this type of modeling in order to understand the exact mechanical behavior that is developed, and also determine how exactly the interventions affect the overall mechanical behavior of the structure based on localized damage and redistribution of damage according, of course, to the location of the retrofitting. Now here we can see the base shear, the maximum base shear, the final loading cycles for the case where we have the infill shear walls. And as we can see, of course, the case where we have carbon fiber embedded rebars derives the maximum, in this case, base shear. And in the hysteretic energy, we found that the glass fiber embedded rebars, the model which foresees the use of glass fiber reinforcement, is the one who derived the highest hysteretic energy. This is attributed to the fact that the glass fiber embedded rebars have the lowest Young modulus, therefore they are more flexible compared to the aramide and the carbon fiber ones. Now, after viewing the results, the question was, okay, what about the cost? So an investigation and a calculation of the total retrofitting cost for each strengthening strategy was performed based on average values found in the international literature, according to the European market. And of course, the cost of increasing the base shear by 1% and increasing the dissipated energy by 1% was estimated. And surprisingly, in this case, we found that we had some negative values, which this tells us that not always the retrofitting will lead eventually to an increased strength and, of course, an increased hysteretic behavior. And again, I remind you, these are results for the final cycles. This means during the preparatory cycles, we have the development of an increased behavior, let's say an increased base shear for the retrofitted structures, but due to the redistribution of the damages and the mitigation, let's say, of the damages, we end up having cases like the BC205, the BC215, and this BC303, where during the final cycles, the mechanical response, the overall mechanical behavior of the structure was found to be lower compared to the initial framing system. So that was a very interesting finding from this research work. So an optimum retrofitting cost factor was developed that takes into consideration, as you can see, the maximum base shear of the retrofitted structure and the initial framing system, of course, and the energy dissipation. So as we can see, these are found here and there in this part. And of course, these CS and CD are two parameters that represent the importance, let's say, in terms of strength and energy dissipation. This means, like, what's more important to me, to have a higher strength, or is it more important to develop and design a structure that will derive an advanced, let's say, energy dissipation enhancement? And therefore, based on this formula, we calculated the optimum retrofitting cost, where we found that if, let's say, we value the same way the increase of the base shear and the hysteretic performance after we retrofit the structure, we found out that the case of reinforced concrete shear wall with aramide embedded rebars was the optimum solution. And of course, we see that these optimum retrofitting cost factor can get negative values, which means that this is an approach. If we apply this approach, we will get negative results instead of achieving what we want. So you can find more information in this publication, which has been recently made available online. Now, another very interesting part, one of my favorite, to be honest with you, when it comes to the cycling analysis of structures, is the dynamic nonlinear response of structures, including the soil structure interaction effect. So in this case, as you can see, we had a publication in 2020 where we investigated the nonlinear dynamic response of reinforced concrete structure, including the soil structure interaction effect. And of course, we use nonlinearities as I described them in the previous slides for concrete, cyclic behavior of concrete. We added the Ramberg-Osgood model for clay, for the nonlinear simulation of clays. And of course, we must also remind here that we also took into consideration the nonlinear mechanical response of the steel rebars. Now, how this research work move ahead, it assumed this two-story reinforced concrete frame that was tested by Garidis at the seismic table, and you can see here the reinforcement detailing. This is the frame that was designed to develop a high ductility behavior. And of course, after modeling this experiment, we were able to capture the behavior accurately. And of course, this specimen was tested under 3 different consecutive accelerograms, which are seen here. And these accelerograms were applied in such a way in order to develop 7 times more load than the actual load foresaw by Eurocode. After we validated the ability of Recon and Fiat to be able to reproduce the dynamic nonlinear response of this framing system, we discretized the soil and we performed some parametric investigations on the soil domain as well. And after we concluded, in this case, on the size of the mesh that we're going to use, we developed 6 different models with different soil types, hard, medium, and soft. And the first set foresaw a depth of 6 meters, and the second foresaw a depth of 11 meters. And of course, after the analysis, the results were compared with the case of the fixed model, and we found out that the maximum base shear was decreased for all cases, and the maximum developed displacement was increased, with the maximum being the case where we have 11 meters depth for the soft soil. M and S stand for medium and soft soil respectively, and of course F refers to fixed. A is 6 meters deep and B is 11 meters deep. Thereafter, we mirrored that model in order to make it look more realistic. So we have a 4-column structure now. We may name it 2H30 frame. And we performed the same investigation by using this more realistic structure for the first accelerogram. So as you can see now, so far we applied only the first accelerogram. In order to investigate what's going on. And definitely, for the case of the horizontal displacement, it's easy to observe that the soft story was the one, the soft soil, model was the one who developed the largest displacement for both cases, 6 and 11 meters depth of soil domain. And we also investigated the vertical oscillation and the vertical base shear. And as you can see here with the black line, the vertical oscillation is initially high at the beginning of the nonlinear dynamic analysis, and then it stabilizes, and therefore this shows that the actual vertical deformation and vertical oscillation does not affect the overall mechanical response, and we did not take into consideration a vertical acceleration. So this is just the beginning of the analysis. We apply the loads and the dead load, the self-weight of the structure, then we have a settlement of the soil, and then this actually oscillates a bit and then it stabilizes. Now, the interesting part was the actual deformation and of course the dynamic response of the structure when the second set of acceleration, the second accelerogram was implemented. So as you can see with the dotted line, this is the soft soil, which at the first accelerogram, it develops a remaining deformation. But when the second accelerogram is applied, the medium soil, the structure founded on the medium soil is the one who actually develops the largest deformations. Of course, we lose the structure there. And this also, here the total base shear, as we can see, the softer model, the model with the soft soil is the one who developed the largest total base shear, which of course created more questions. We say, why is that? And this is the reason why we actually performed the same analysis, and on each and every dynamic nonlinear step, we calculated the first fundamental period, the first eigenfrequency, as you can see here, during the analysis, and we compared this with the actual typical frequency of the soil domain, and we found out that around 9 seconds, the medium soil has a frequency of 5.096 hertz, which is close to the 5 hertz of the eigenfrequency of the superstructure, and therefore this explains the reason why the medium soil, the model that is founded on the medium soil domain, developed those large deformations. And of course, this is just a very small example of how complex the soil structure interaction phenomenon is, given the fact that here we have just a squarish structure, a very simple structure, two-story structure with isolated footings. Everything is according to, like we civil engineers like them to be, normalized and square, right? So imagine if we investigate a problem with a more complicated geometry and piling foundation or other types of foundation that will make the soil structure interaction phenomenon even more complex to capture numerically. And of course, again, this illustrates the importance of developing this type of tools in order to be able to investigate and understand deeper and develop a deeper understanding on how these problems behave, and of course the overall effect of the soil structure interaction, starting from the local effects, ending up at the overall mechanical response of our structures. Now, when it comes to machine learnings, we're done with the cyclic analysis and the validation. The next step is to have a step backwards, actually, and say, all right, we have this tool, what do we do with that? We are able to investigate different types of problems, so how can we utilize it in order to help develop methodologies through which we will be able to provide civil engineers with the ability to design safe structures. So the main idea here is to develop data sets by replacing the actual experiment by using, of course, recon and fair, and performing nonlinear ultimate analysis and capturing different features of structures, and then use the machine learning algorithms in order to develop models that, of course, help us to connect a set of inputs with a specific set of outputs. We have different algorithms and methodologies like linear regression, higher order regression, random forest gradient boosting, and of course artificial neural networks. And we have other methods or modifications of these methods as well. Now, what's the main problem? One of the main problems, of course, here of these methodologies is that we do not have a method that will say, yeah, if we use this method, it will give us good results regardless of the data set. So this is not yet a problem that has been solved. So we need to use different types of machine learning algorithms in order to find which one fits best and has the ability to give us a result and predict the results for out of sample cases, right? So this is known as extendability. Now, this project that I'm going to show you here, the results from this project, has as a goal to predict the shear capacity of reinforced concrete slender beams without stirrups. So you can see there the mesh of one of the models that were used. We use here 20-noded hexahedral elements, and we used, of course, the embedded rebars for the reinforcement. And we generated, in this case, 20 new geometries ranging in terms of length, section width, and section height. And of course, the reinforcement ratio, different reinforcement ratio. And for each and every new geometry, we run an analysis for 500 different material and reinforcement combinations. So we generated a total of 10,000 models that were, in this case, analyzed through the use of Recon and FAIR. And we developed a closed form formula, which is shown here. And thereafter, by the way, the training was performed and the testing by using this data set that was developed in a digital manner, right? We didn't use a single experimental data, and then we developed the formula, we tested it again on digital data, and then we got 36 experimental data. So we got 36 reinforced concrete beams that they were experimentally tested, and we used the proposed formula to check on whether we have the ability to actually predict the strength of this type of specimens. And this is the comparison between the experimental shear strength and the predictions from the proposed formula. This is the proposed formula with 10 terms. As you can see, it's pretty longish. And of course, compare the mean average error. As you can see, the 10-term formula derived a 47% error, and the Eurocode and the new ACI into 2019 derived a 113 and 146 approximately percentage error. So this shows the possibilities here and the ability, let's say, in the future to develop even more accurate formulae and replace the semi-empirical formulae that are currently valid and used by thousands designers across the world. Now, another very interesting upcoming publication is titled High Performance Deep Learning Algorithms for Structural Engineering with Professor Papadragakis and Dr. Nikolaos Bakas. And in this case, we use parallel training. So we developed an algorithm that is able to train in parallel, and we used an older data set of around 800 plus analysis results. And of course, you can see the statistical metrics here of independent variables. And we were able to train by using deep learning and artificial neural networks to train a new advanced model. This is here the number of GPUs used versus the speed up on Cyclone. Cyclone is a supercomputer that has 64 GPUs, Tesla GPUs. And as you can see, the scaling is pretty amazing. It's almost linear. So the more GPU we use, the fastest the actual training gets. And definitely, you can see here the time required to train and develop the model. Now, as I said, Cyclone has 64 Tesla GPUs, and the cost of each GPU is 10,000 euros. So this means that when we were running 64 GPUs at the same time and we were engaging them in our analysis, we are using like 640,000 euros at the same time. I don't know about you, but this is pretty cool. And here we can see the Drawbar Effect on the loss function during the training in parallel. And these are the results with low dropout. So the idea here, given that, by the way, given that this is not, we did not publish this yet, I will not go deeper until we get the publication out. But just the idea is to get the data set, break it into smaller data sets, and then use that to train in parallel. And there is a communication between the data sets. And of course, managing to develop a predictive model that is has 50% lower error compared to the older model that we've developed through the use of an algorithm that I will show you in a bit. We use the same parallel algorithm and run it on the high-performance computer in order to develop a fundamental period formula, in this case, for reinforced concrete structure. So this formula has the ability to predict the fundamental period of reinforced concrete structure with soil structure interaction as well. So either fixed or with soil beneath the structure and the foundation. Of course, in this case, we were able to decrease the error on the validation set by 22%. A new project that is currently...
Sorry, George, please, just a couple of minutes left.
Yeah, I'm done.
We have time for question as well.
Yes, of course. This is the algorithm that was used for the case of steel structures, and we can see here the minimum and maximum values in terms of height, length, and width of the structure that was used in order to develop the formula. And these are the modes as they resulted from the analysis. 1,152 points were created, and of course the depth of the soil, the young modules of the soil, height, length, width of the soil. Some extrapolation parameters were used in order to develop the proposed formula. This is the, as you can see, the comparison between the proposed formula and the numerical and the data set, 99.95% correlation ratio. And we developed additional 168 results that they are out of sample, and we found a 99.71 correlation ratio, and of course 2.8% mean absolute error compared to Eurocode and other formulae out there. So in this case, this is the actual formula. It looks very longish, right? But don't forget, we have this, like Excel applications, we can program this, just add the input, and automatically we will get our results. All right, thank you. I will not talk about the future work. Let's give some time, some space for questions. Thank you very much.
Thank you, George. Thank you for your very important, interesting presentation. Congratulations for your research. I'm asking, Iman, do you have any question on seismic field? Iman.
You caught him at the bad time.
Track. Bottom. Okay, maybe Iman is busy.
Yeah, George, I have a practical question, I guess, on the test that you were showing for the retrofitting using infill shear walls.
Yes.
That you were using different type of internal reinforcement for those walls.
Yes.
How did you connect? Was this supposed to the reinforcement in the infill walls? Is it connected to the structural elements of the pre-existing structure?
Yes, there is a way where you can drill the beams and the columns, the existing beams and columns. Let me bring this forward. And you can drill and use duals, right? And then connect them. This is what they did with the steel rebars, and they use epoxy materials, and then they use formwork and concreted, and they use and filled it with concrete.
So they did connect them. They drilled and epoxied them into the other elements.
Yeah, this is what was done for the steel rebars. Okay, the steel reinforcement in the surfing project. And of course, what we did was to model that and capture the results and validated that we have the ability to capture it. And then we got the same numerical model, and we converted the material properties of the embedded rebars from steel to carbon, glass, and aramide materials.
And
so everything was done numerically.
Yeah, and you were using the same area, or were you using? Okay. So you were just replacing area of steel with area of reinforcement, and depending on the properties.
Bravo! And we also calculated the actual cost if we have used that material. So one might say, okay, why don't you use the same strength, so you will need less area for the carbon, fiber,
or the same stiffness in this case.
Yeah, but the idea is to compare the cost effectiveness in terms of what the strategy offers, right? So if the strategy offers high strength but has high cost as well, then overall value for money, let's say, is average. If it has a low cost and high increase of strength and high static behavior, then definitely this is a better approach. So this was the main objective of this research work.
Okay, thank you.
Welcome.
Andreas?
Yes, thank you, George, for the very interesting presentation. One question for the modeling of the joints was a few slides before the one you were there. So you, as far as I understood, you simulated the cyclic loading, the degradation due to cyclic loading of concrete with the damage factor. Am I right?
Yes, correct.
And did you do the same for steel in this case?
Yes, both materials get, let me find the damage factor.
The damage, I remember you had at some point in your presentation. And did you also do the modeling of the bond between the materials?
This is the big advantage of this approach, is that you do not need to model the actual bond by adding an additional degree of freedom. Mm-hmm. So we escape that, given that it creates a lot of numerical instabilities. And we found out that this damage factor, which is directly connected to the number of opening and closing of cracks of the concrete material that surrounds the embedded rebar, gives us the ability to capture realistically the overall mechanical response, and of course, phenomena like pinching, which were shown here.
So these damage factors take into consideration the bond between the concrete and the steel, right?
In an indirect manner, it's this damage factor takes into account, let's say we have a hexahedral element over here, right?
Mm-hmm.
So if you have a hexahedral element here, then there is this rebar which is embedded within this.
Okay, you take practically at the bottom where is the largest effect.
Exactly. So you say how many opening and closing of cracks do I have in that finite element, in that hexahedra? And what embedded rebars are found in that region, and then you go and affect and change the internal forces transmission from the embedded rebar to the hexahedral element, and therefore you take into consideration the effect of the damage of the concrete, because at the end of the day, if the concrete is damaged, then you will have slippage, right? So this was a numerical methodology that was developed in order to take into consideration in a direct manner the state of the concrete material, and calculate in this way the actual effect on the contribution of the embedded rebar to the concrete. Because you have an embedded rebar, you calculate the stiffness matrix, and that stiffness matrix is added on the stiffness matrix of the hexahedral element in a direct way after you transform it. So if you affect the stiffness matrix by affecting the Young modulus of elasticity of the embedded rebar, then the hexahedral element is also affected, and the contribution of the embedded rebar is also modified, and then you have the effect of the overall mechanical response of the structure.
Okay, thank you, George. And one last question, if I can. Did you also do the modeling of the strengthened ones in this case?
Yes. These are the results over here from the strengthened one. So as you can see, this is the model.
Oh, in this case, did you model the interface, or did you do anything like that, or there was no need?
There was no need, because the failure occurred due to the crushing of concrete and not due to the loss of the strengthening of the CFRP. But that's a point. But again, if you think a bit holistically, let's say, in order to reach your structure or that joint to a point where the CFRP sheet is going to fail, then it means the concrete is already severely damaged. So either you capture that state or not, I think it's not that important. But definitely, if you take into consideration the interface and the slippage that occur, you will be able to reach to more realistic results. But it depends on the level of accuracy that you're looking for. And in our case here, we are looking for a model that will allow us to go to this type of models, like the one that we show here.
Very interesting.
This is a full structure, and this is an actual real specimen that was tested under the surfing project. So you will not find any research projects, any publications that they actually model the entire building as it is. And one might say, isn't it symmetric? The answer is no. Actually, the reinforcement used for these infill shear walls and the reinforcement on the other side, north and south, they are different. So there is asymmetry. Most researchers, they just do it 2D. And they use 2D models to capture it, and they barely capture it. So what we did here is fully 3D, and then we took it a step further.
Thank you very much, George. Very, very interesting. Thank you.
Thank
Most
you.
welcome.
Giacomo?
Yeah,
Please.
thank you. Hi, George. Giacomo, also from Sheffield. Nice to meet you. Thanks for the presentation. Very nice. Just very quickly, I guess, just a couple of questions. I was curious about the damage model. So I guess I'm reconnecting to Andrea's questions. Is the model non-local?
No, it's absolutely local, because what you are looking here at is the constitutive material model, the constitutive material matrix of the concrete. Okay, so this means that this applies at each and every Gauss point. So you have a hexahedral element with 8 Gauss points. So these are your 8 points, your control points. And at the material level, you are adjusting your material properties based on the damage level. So from that material level, you calculate the stiffness matrix of the entire hexahedral element, and from each and every hexahedral element, the stiffness matrix and that will control the overall mechanical response of your entire structure. So this means that you look at the material and the behavior of concrete at the material level, and then from that you get an objective, let's say, calculation, given the fact that you are working at the material level, calculation of the overall mechanical response of your structure. This is not like a beam column finite element that will say, I have a hinge there and the entire section will behave like this. So this is the complete opposite.
Okay, so there isn't any energy-based criterion to spread damage or anything like that?
No, everything is done according to your stress state and the strain state of each and every finite element.
Right. Can I ask another one, Francesca?
Yeah, of course.
Yeah, just connected. What happens here?
You have to.
If the direction of the crack rotates. So if the material cracks like this first, and then there's a rotation, say, of 90 degrees.
Yes, the cracks are calculated, and their rotation are calculated based on the stress, the principal stresses. See, there you go. All right, so what we do, we have 6 tensors, right? Normal stresses, x, y, z, and shear stresses, x, y, y, z, z, x, okay? You solve the eigenvalue problem and you calculate the principal stresses, sigma 1, 2, and 3. And you know their directional cosines. And then you find the maximum tensile principal stress. And you say, along that direction, the crack will be perpendicular to that maximum principal stress. So you calculate it based on the stress field. And then that crack remains open until it closes. So if you have in another step, let's say, to recalculate, and you find that the crack direction is changing, you are not rotating the crack, because you say, in reality, if I have a crack opening, it's a crack opening. It will not close and then reopen a bit lower or a bit higher, unless you have a second crack opening. So you will have this case here, as you can see. So if you have 3 cracks, then you say, this is crash. It means we lost it, and therefore we're going to use, in this case, this matrix, this material constitutive matrix, where we have a remaining strength due to gravel interlocking and friction and so on. Therefore, we will not assume that this is completely 0, and that's it.
Okay. But do you have one single scalar value of damage for every point in space, for every Gauss point, say?
Yeah, for every Gauss point, you calculate the damage factor and you apply it within them.
And it's a scalar.
Yeah, and it's a scalar. And also, of course, in order to determine the crack opening, you use the failure criterion here each and every time.
Okay. Yeah, very interesting. Thanks very much.
Most welcome.
Well, thank you everyone for joining this seminar. Thank you, George, for your presentation again.